Stripping down science. The Naked Scientists.
Hello, it's Sunday, December the 12th. Welcome to The Naked Scientists with me, Ben Valsler.
And me, Dave Ansell.
This week, we're looking at an exciting and new material, graphene.
Graphene is a carbon lattice just one atom thick. It has some amazing physical and electrical properties, and the scientists that first discovered it were honoured with a Nobel Prize just this year.
We'll be finding out how it's made, and we'll discover how it could soon be making flexible computer screens, it could be protecting rockets from lightning, and it could become the basis of super-fast computer chips.
In the news, we'll be hearing about a new super high-density capacitors, a database to let you see the world as a bee sees it, and the first spacefaring cheese.
If you have any questions for us about spacefaring cheese or anything else, then we would love to hear from you. If you'd like to get in touch through Twitter, you can just tweet at Naked Scientists. You can write on our Facebook page, we've a link to that at thenakedscientist.com/Facebook, or you can drop us an email. Our address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with me, Ben Valsler, and with Dave Ansell. And first up, we're going to take a look at some of the week's biggest scientific breakthroughs. Dave, your first story is actually extremely relevant to a show about graphene.
Indeed it is. Now, scientists have come up with a new form of supercapacitor. There are two main traditional ways of storing electrical energy. You can either use a rechargeable battery to store the energy chemically, which will store a lot of energy, up to about 350 watt-hours per kilogram. It will do so quite slowly and for a limited number of recharge cycles, so it might take a couple of hours to charge up your rechargeable batteries. The other option is to use a capacitor. This, in a simple case, is basically two sheets of metal with a layer of insulator in between. If you apply a voltage, some charge will flow onto the sheets and will be attracted to the opposite charge on the other sheet, so making it a bit more stable. Capacitors have the advantage that because they're not using chemical reactions, they can charge and discharge thousands of times faster than batteries, and they waste much less energy as heat. The problem is that conventional capacitors store less than a thousandth of the energy of batteries. To increase this, you need to reduce the distance between the charges, stabilising them and allowing the capacitor to store more charge and therefore energy at the same voltage. Recently, by using activated carbon filled with an ionic liquid as an electrolyte, ultracapacitors have got this to about as good as lead-acid batteries. To improve this, you need to increase the surface area of the electrodes. Now, Chengguan Lu and colleagues have used graphene, which is essentially a single layer of graphite, a single atom thick, as the electrode. This is about as thin as an electrode can possibly get. It's only one atom thick. And they've altered the graphite so that it's curved and so they won't lie flat and stack. This means the ionic liquid electrolyte can get in between the layers and produces a very efficient capacitor. They can store between 80 and 136 watt-hours per kilogram, which is about as good as a nickel metal hydride battery, which were the standard batteries about 10 or 15 years ago. This might not sound very impressive until you realise that it would charge in seconds or at the most a couple of minutes, as opposed to the hours for a lithium-ion battery. This would both allow a car to charge up as fast as you normally fill up with petrol, and make it ideal for storing the large amounts of energy very quickly, such as when you brake hard in a hybrid vehicle, so you can regenerate that energy and use it later.
So that not only gets around one of the problems with electric cars, which is that they take hours and hours to charge, but it also makes better use of a technology that we've already got in place, this regenerative braking, where we steal back some of the energy that we would otherwise just be wasting when we hit the brakes.
That's right, if you brake really, really hard, the amount of energy which is coming back in through the regenerative brakes can be just too much for a battery to store, and so it gets wasted.
Thank you, Dave. And now a new database, very friendlily named Fred, could help to establish how bees see flowers and help researchers understand more about one of the world's most important pollinators. Bee vision is very, very different from human vision. In fact, they perceive colours that we are simply incapable of seeing. Most insects have light-sensitive cells or photoreceptors that are sensitive to ultraviolet, blue and green light, and many have 4 or more receptor types, allowing them to perceive a wide range of wavelengths, from the long to the very short. In comparison, human eyes are simply not up to the job of assessing flower appearance objectively. Now, for the first time, a database has been developed that collects an extensive range of data on the full reflectance spectrum of flowers and has been made freely available online. Publishing in the open access journal PLOS One, Sarah Arnold from Queen Mary University of London and colleagues announced the creation of FRED, the Floral Reflectance Database, which contains the reflectance spectrum, or how much light is reflected at different wavelengths, for flowers from all over the world. To really understand the environment as perceived by an insect, you also need to know which wavelengths that particular species can detect. And this is also included in FRED, allowing researchers to create what's called a colour space for an insect, observing flowers specifically from that species' perspective. Now, FRED is set to grow as its users provide more reflectance data from different species in different habitats, and although so far their priority has been bees, people will improve the catalogue of insects that are available. And as FRED contains data on flowers of different ages but from the same species, it can also be used by botanists to research global trends in flower colour, to research plant growth and plant development. It can be used by ecologists studying habitat diversity and interactions, as well as researchers who are trying to understand the vital role that pollinators play in our environment.
So if we know what a bee sees, does that mean that we might be able to learn what a bee likes and therefore know how to attract them to, say, your nice fruit tree with lots of flowers on it?
There's already been quite a lot of work that actually tells us what it is that bees look for in a flower, and we know about these nectar guides, which are lines and colours that we can't see that indicate where nectar might be found. But for the first time, this really collects the raw data about a wide range of flowers so that we can genuinely look at it without the filter of human perception, and we could sample a whole field and understand where there are pockets that bees see the same as us, where there are pockets that appear very boring to bees, and start to get a better idea of how the ecology works together, how the pollinator and plant interactions really work. Now, Alzheimer's disease is a common cause of cognitive decline amongst elderly people. An estimated 1 person in every 5 over the age of 80 is affected and develops a range of symptoms, including memory loss. The cause of the disease is a build-up in the brain of a protein called beta amyloid, which damages nerve cells. But why does this happen? Chris Smith spoke to Randy Bateman, a neurologist at Washington University in St. Louis.
So there was a basic question which we began to consider about 4 or 5 years ago, and the question was, what causes Alzheimer's disease? And that question has been asked for a long while, but this was more directed at the current thinking about what causes Alzheimer's disease in relationship to what's known scientifically. And there's an amyloid hypothesis which specifies that buildup of a protein called amyloid beta, which is normally made by our brains, that this increase in this protein in the brain leads to damage that causes the symptoms of Alzheimer's disease. Now, the basic question that we were asking was, in Alzheimer's disease, does the amyloid beta build up there because it's being produced too much or made too much in the brain, or is it there because once made, the brain has a problem clearing it away? And so this comes as some of the basic information about amyloid beta is that the brain normally makes this. The neurons or the thinking cells of the brain normally produce this amyloid beta protein in the brain, and it's normally cleared away, and it doesn't build up into very high amounts. But what we also know is that in patients that have Alzheimer's disease, their brains are filled and littered with this substance to 100 to 1,000-fold normal levels. So it builds up at very high levels, and this is thought to be toxic to the brain and cause damage, ultimately culminating in dementia of the Alzheimer's type.
So you've got 2 problems there. One of them is it that there's too much being produced, or is it that it's not being dispensed with, dealt with by the brain as it is in a healthy person's brain? So how can you try and disentangle those 2?
That was the challenge, and that's where the technique was actually developed to answer this question. And essentially, the way to do this is actually to label the proteins as they're being made so you can track them. And in that, once a protein is labeled, then you can track how fast it's being produced and how quickly it's being cleared away. The first publication of the method itself was in 2006, where we reported what normally happens in young healthy people with amyloid beta in the brains in terms of its production and its clearance rate. And oftentimes I use an analogy that this labeling system, imagine that you have a sink of water and you have a faucet on with water coming into the sink, and you have a drain that's draining the sink at the same time. If you just look at the sink and you don't look at the faucet or the drain, you only see a level of water in the sink, and that's what we normally measure when we sample the fluid that surrounds the brain. We measure how much of that amyloid beta protein or the water level is there. And so one way to track how fast it's coming in is you can imagine that if you dyed the water coming out of the faucet a certain color, say blue, that the water in the sink would turn bluer and bluer over time the more blue water came into it. And if you watch over time how much of that water has been labeled with that, in this case, a color label. In the case of the amyloid beta protein, we're using a label that's just slightly heavier for the protein. Then we can estimate how fast the production or the rate of water coming into the sink is. And by the same token, if you stop labeling and then you watch the water as it's cleared away, as new, fresh, clear water comes in and the blue is cleared away, you then have an estimation of how fast the sink is draining that water. And so this is what we do. We take a label that incorporates into the protein. It's an amino acid, which is a building block of proteins which our body normally makes, and it's slightly heavier than normal amino acids. We infuse that into the bloodstream of the person, and all the proteins that person is making can be tagged with this label, marking it as newly made. And then we sample over time the fluid that surrounds the brain. It's called cerebrospinal fluid. And we watch the appearance of this newly labeled amyloid beta protein, and then we stop labeling, and we watch how that labeled amyloid beta is cleared away over time.
And you did this in healthy people, and you did this presumably in a group of Alzheimer's patients to compare the rates of production and removal of the beta amyloid in the brains of both.
Exactly. And so in this study, what we did is we compared 12 people who have Alzheimer's disease compared to 12 people who don't have Alzheimer's disease but are about the same age, and we compared the two to find that there was a significant decrease in the clearance of amyloid beta, but on average there was no significant change in the production rate of amyloid beta.
The only problem with this study is that it tells you about people who've already been diagnosed, and it would be very interesting to wind the clock back in their lives or look upstream, look in people who are going to develop Alzheimer's disease, or just look in people who are viewed as healthy, and then follow them up and then see who does get Alzheimer's disease and see if there's anything lurking upstream in those people.
That's exactly right. That's an insightful point, and one which we're planning on doing. As the study goes on and participants come into the study, we're in fact following each individual over time clinically, so that the cognitively normal people that have done the study, they don't all have exactly the same production and clearance rates. Some are faster and some are slower. And so the basic question is, are the people who have slightly impaired or impaired clearance but are cognitively normal now, are those people at increased risk of getting the disease at some point in the future?
How do you know that the people who have got the Alzheimer's disease now haven't just got a reduced clearance because the disease has in some way damaged the brain, and the reduction in nerve cells that is associated with Alzheimer's disease has just impaired their ability to get rid of it, and that's why you're seeing that as a consequence of the disease process, not so much as a consequence actually of having caused the disease?
With the current data, there's no way to distinguish between those two possibilities. And although we may hypothesize that, for example, decreased clearance may lead to increased levels of amyloid beta and plaques, that's not demonstrated in this particular study. That's the point of doing the ongoing research, is to determine if that's correct or not.
Randy Bateman, a neurologist who's looking for a way to knock Alzheimer's disease on the head. He was talking to Chris Smith and has published that work this week in the journal Science. Dave?
Brilliant. Now, here's another example where learning from nature might be useful. Apparently, glider pilots should be learning from falcons. gliding in all its forms has become a relatively popular pastime, and if you want to glide for anything more than a few minutes, you've got to take advantage of thermals. These are areas of warm air rising amongst the colder air surrounding them. If you keep your glider inside this column of air moving upwards, you'll be lifted up without having to do any work yourself. The problem is, of course, that air is transparent, so you can't see the thermals. And so you're just restricted to feeling their effects. So glider pilots have learnt various rules and worked them out so the glider stays inside the thermal. Essentially, they spiral around and around, and if the rate at which they're climbing increases, they make the spiral a bit larger, because that means they can get their wings flatter, and therefore they're dropping through the air slightly slower. And if their rate of climb gets worse, they try and turn a bit tighter, which will pull them closer into the centre of the thermal. This system works really well if you have a really nice clean circular thermal, but if there's a lot of turbulence you can get temporary updrafts, which is really easy to confuse with a real thermal. So the glider pilots can get just entirely confused by these little temporary updrafts, and they're left in the middle of an area with no uprising air, and then they might end up on the ground in the middle of nowhere. They've got to call in their mates to pick them up.
Which is precisely not what you need when you're gliding, of course.
That's right. Now, Zsuzsa Akos and colleagues at Eötvös University in Budapest have been studying the flight of peregrine falcons, essentially by attaching GPS receivers to them. They've noticed that rather always spiralling in one direction, they occasionally swap the direction which they're spiralling in. Now, this sounds really stupid because it will cause them to leave the nice thermal they're in already. But in very turbulent air, this means they can test a larger volume of air for other better thermals. If they find a better one, they'll stay in it. And in computer simulations, it turns out to be a much better strategy than the conventional one. This is, of course, of interest to glider pilots, but also to manufacturers' unmanned air vehicles, which are used to kind of study the ground, so you've got cameras on to see what's going on all the time. And they could save an awful lot of energy by soaring rather than having to run their engines all the time. And nice simple rules like this allow them to soar without using up all the energy calculating where they should be going next.
Thank you, Dave. Observations made by the Keck telescope in Hawaii have confirmed a fourth planet orbiting a nearby star, but have thrown current theories of planetary formation into doubt. Publishing in the journal Nature this week, Christian Mawa from the Herzberg Institute of Astrophysics in Canada and colleagues in the United States have analysed near-infrared images of the star HR 8799 and found a new exoplanet to add to the three already previously discovered. These planets have particular properties that make this sort of imaging possible. They're very massive. The new one is somewhere between 7 and 10 times the mass of Jupiter. They're a long way from the star itself, over 25 times the distance between the Sun and the Earth. That's 25 astronomical units. And they're relatively young, less than 100 million years old. Younger planets are still hot from their creation, which makes them glow brightly in these near-infrared frequencies. Now, finding new planets is always fascinating in itself, but the really interesting thing about this system is that it doesn't fit with current models of planetary formation. There are two models that describe the formation of giant planets like this. There's the core accretion model, where small bits of rock collide and gradually clump together until that lump has enough mass, and therefore enough gravity, to hold onto an atmosphere. And there's also the disk instability or gravitational collapse model, where variations in the disk of material around the star, that's called a protoplanetary disk or a proplet, will condense out to form balls of gas that then gradually collect dusty matter at their core. In the case of the HR 8799 system, the innermost planet could well have formed by core accretion, but those further out would actually need far longer to do so. In fact, they'd need more than the age of the star itself, so obviously that can't have happened. So we look to the disk instability model, but in that case the protoplanetary disk would not have been in the right condition to allow the innermost planet to form back when it did. So how did these planets get there? Well, right now we just can't be sure. The authors say that a hybrid process with different planets forming through different mechanisms cannot be ruled out, but seems unlikely with the similar masses and dynamical properties of the four planets. The other option is that planets formed elsewhere and then moved into their current locations. But the thing is that until we find more systems like this one, we simply don't have enough information to be able to make this decision. But with exoplanets being discovered at a frankly astounding rate, we may find more of these planetary families soon.
Now, again, on the space theme, an American entrepreneur has launched a cheese into space.
A cheese.
A cheese. A wheel of cheese.
An actual edible cheese.
An actual edible wheat cheese. Great big one, couple of feet across. Now, SpaceX is a relatively small Californian-based company, and it has just launched a wheel of Le Bruyere cheese into space. And more impressively, brought it back down again after 2 orbits. Why? Essentially just because they could.
So why not?
Exactly. The really impressive thing about SpaceX, which is a relatively small company mostly owned by Elon Musk, who made a fortune out of PayPal and decided to spend the money essentially building space rockets to try and get our civilization into space, is that this company has both built the Falcon 9 rocket themselves and the Dragon space capsule, which brought it back down again. And this is particularly interesting because the capsule is designed to be able to carry 7 people at some point in the future when they've done a few extra safety attributions and when the rocket is known to be a bit more reliable. And for now, SpaceX are concentrating on using the Dragon capsule to take cargo to and from the International Space Station. The cheese was sent up because they needed something to act as a payload, and it's an experimental rocket and no one's going to put anything really valuable on there. And there was no reason not to send a cheese. I think it's rather refreshing and positive for the space industry that someone is in a position to send some cheese into space just because they want to.
And I guess that's because, of course, with every mission we've sent so far, every single gram that we send up there has to be accounted for. It has to do something for us. And so frivolities like cheese has just been something we haven't been able to think about.
That's right. And the organisations are very large and bureaucratic, whereas this is essentially a small startup company and Elon Musk is in control. And so if he wants to send some cheese up, he can.
And I guess the really important question about this was there any ill effect to the cheese? How did it taste afterwards?
I don't think anyone has eaten the cheese yet, but I'm sure it's now an awful lot more valuable than it was before they launched it up there.
Thanks, Dave. If you'd like to know anything more about any of our news stories this week, you can find them on our website at thenakedscientists.com/news.
Keeping you abreast of the world's best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
Still to come, we explore the different ways to make graphene and find out how it could become the basis of ultra-flexible touchscreen displays.
But first, it's time for this week's episode of Planet Earth, and we're looking at one of Britain's best-loved mammals. That's the elusive red squirrel. They've been under threat from a squirrel pox for a number of years, and in 2008 the virus decimated numbers at one of the few remaining reserves at Formby near Liverpool. Sue Nelson visited the reserve to find out more about a 4-year scientific project aimed at understanding squirrel immunity and improving red squirrel conservation. There she met Julian Chantry from the University of Liverpool School of Veterinary Sciences and researcher Tim Dale, who was carrying a bunch of very long wire cages.
We've got 4 of the traps we use for the squirrels. They are in fact mink traps, but they generally sort of use the same principle.
So they're basically just a long rectangular wire cage, aren't they?
That's right, with a pressure plate in the back, has a trigger that allows the door to spring shut when that pressure plate goes down. We usually bait the back of the trap with peanuts, maize and black sunflower seeds are quite favourable.
Where do these go?
These go, we've got 2 tactics for catching the squirrels. One goes on the floor and the other one goes on the tree trunk vertically. They tend to work better for red squirrels, whereas the ground traps work better for greys.
And once you've trapped the squirrels, what do you do then?
The first thing to do, because as first concern is the welfare of the squirrels, and just cover the trap. It tends to calm them down. They don't feel as frightened then. And then we'll get all set up with his equipment to sort of handle and sample the squirrels.
Julian, once you've got a sample of blood from a red squirrel, what are you looking for?
We're looking for antibodies to the squirrel pox virus, which shows that these squirrels have survived the epidemic back in 2008 and now have antibodies, a degree of immunity to this virus.
And so far, Tim, what have you found?
We've found a small number of the population that do seem to have antibodies to the pox virus, which is certainly promising news, because it does say that a vaccine might be a viable option. In terms of numbers, it is a very, very small percentage, so it isn't the answer to the red-grey squirrel disease problem.
When you say red-grey squirrel disease problem, is this because a grey squirrel's immune to this virus?
Effectively, yes. It seems that the grey squirrels brought the squirrel pox with them when they came over from America. And because the grey squirrel has evolved with that virus for a long time, it doesn't cause any clinical disease. So they're able to carry on normal life without it affecting them.
It sounds as though this is potentially good news for the red squirrel population, Julian, but I do sense, particularly from Tim, a touch of caution there.
Yes, it's perfectly right. You've got to be a bit cautious when you interpret these blood results. It's good that some of the squirrels have encountered the virus and survived and now have antibody, but that doesn't necessarily mean that they are immune. All we can do is monitor the population as we are trying to do, making sure that their body conditions, so their weight and their fat reserves are up to standard for them to survive the forthcoming season. If another outbreak occurs, you'd hope these squirrels will be the ones that survived and their offspring, but we just don't know without monitoring the group.
Tim Dale, you've got a brown cardboard box here at our feet. What's inside?
What we've got here is one of the red squirrels that we've chipped and sampled. When I say chip, that's an ident chip, so we can identify each individual squirrel that we've caught in the past, and we're about to release it after its experience with us.
OK, right. Are they quite shy creatures?
Definitely. Generally, we'll have to be reasonably quiet now, so we don't.
OK, you're opening the box. It's like lots of dried hay and straw in there. Gently moving it. Oh my goodness. Oh, it is small, isn't it? Oh! There it went. Up a tree. That gave me quite a fright there. It suddenly scarfers, doesn't it? Yes. Wow.
Yeah, they don't hang around. They're fast little creatures.
Yeah.
Tim Dale and Julian Chantry from the University of Liverpool celebrating the release of a healthy red squirrel with Sue Nelson. You can download the latest Planet Earth podcast as well as find links to Planet Earth online on our website at thenakedscientists.com/Planet Earth.
We're talking about graphene this week, so to get a bit of background on what graphene is and how it was first discovered, I met up with Mira in an engineering lab at Cambridge University.
This week on Naked Engineering, Dave and I have come along to the Cape Building, which is part of the engineering department here in Cambridge, and we're here to learn all about graphene. Now, to start things off, Dave, what really is graphene?
Well, I'll start off with something much more everyday. It's a pencil. Now, down the centre of a pencil, you've got what people call the pencil lead, but that isn't made out of lead, it's actually made out of graphite. This is a form of carbon, and when you write with the pencil, it comes off and leaves a mark on the page. Now, part of the reason why it writes so well is that graphite is very, very slippery. This is because it's made up of lots and lots of layers all piled up. And the layers themselves are very strong, but the bonds between the layers are quite weak, so they can slip past one another, and it's a really good lubricant. Now, graphite's been around for hundreds of years. People have known about it. People have made pencils out of it. It was only recently that people realised you can actually take one of these layers, a single atom thick, and separate it, and that's called graphene.
And, well, one of the places where this graphene is being made is here in this clean room, and it's being made by Andrea Ferrari, who's a reader in nanotechnology, and his team here in the engineering department.
Special about graphene, there are two main things. The first one is a truly two-dimensional material. We had nanotubes before. Nanotubes were rolled up graphene sheets. It was quite unexpected to have a single layer and for it to be stable. The second thing that is very special about graphene is the combination of optical and electronic properties. So the electrons of graphene behave as massless particles, which means that we can have a very huge mobility and extremely good electronic properties compared to any conventional semiconductors. And the second part is the optical properties, that even being a single atom thick, a single layer of graphene can be seen by eye and absorb 2.3% of light.
And, well, now an interesting aspect of graphene, though, is just how it's actually obtained from graphite in the first place, because it is just a single atomic layer.
Yes, the first method we're going to see is the one that was originally developed at the University of Manchester by Andergheim and Costiano Voselo. It simply consists in taking a piece of graphite, a piece of tape, and peeling it off until you get a single layer. And Antonio is going to show you how to do it.
Okay, and yes, so with us is Antonio Lombardo, one of Andrea's PhD students.
Okay, I'm going to take one of these small pieces of graphite. I'm going to put them on top of a sticky tape. I use another piece of tape just to clean, in a way, the surface of graphite many times until I get a nice and uniform distribution. So once I'm happy with the graphite to be on top of the tape, I just take one of these small silicon chip. These are covered in 300 nanometers of silicon oxide. Once we put the silicon substrate on top of the tape, there is some interaction in between the top layer of the graphite and the silicon surface. At the end of the process, we have many different layers. This part is just one single atom thick.
And it's just a remarkably simple process, which, I mean, you could literally do this at home if you had a piece of tape and a lump of graphite.
So now, having found out how graphene can actually be isolated, we've now come out to find out ways that it can actually be used. So we've come to one of the optical laboratories still here in the Cape building. And so, Andrea, what are some of the applications of graphene?
Clearly, the first thing that people thought about was traditional electronics, replacing transistors, and this may come in the near future. However, we are focusing here on applications that may come in the next few years, maybe 3 to 5 years. And one is, for example, flexible electronics. So we can integrate graphene with plastic to make transparent and conductive materials that can substitute screens in laptops and so on.
So because graphene's so thin, it almost has to be flexible, so it's a very flexible material.
Absolutely. Graphene is extremely flexible. It doesn't break. I guess if you take a piece of silicon and you flex it, you will break it. Graphene will never break. In fact, in plain graphene is stronger than diamond, but still it maintains the exceptional electronic and optical properties at the same time. So that's why it's an ideal material for flexible electronics.
Well, you've got an example of one of your flexible electronics here in front of us. Well, it looks like a piece of plastic, really, about 8 centimetres squared.
It is, in fact, a piece of plastic, actually 2 pieces of plastic, and we put graphene on the top of it, and in between them, some liquid crystals. We use graphene because it's conductive, plastic is not. We apply voltage to the graphene, and the graphene switches the liquid crystal on and off, and lets the light too.
So the graphene on the 2 pieces of plastic are essentially attached to a battery of some kind. The 2 layers of graphene are applying quite a large voltage to the liquid crystal in the middle, which is changing its optical behaviour entirely.
And in fact, the plastic is just there as a container for the liquid crystal. It does nothing at all.
So at the moment, then, it's a bit misty, and it's placed over some writing on a piece of paper. You can't quite read the writing because of the misty screen.
Now we are going to apply the voltage, and the writing will appear.
Yeah, it's very clear.
Yeah, it's very clear. It will become a completely clear window. And in fact, utilizing a slightly different technology, we can also freeze it. So it's quite possible to freeze it on or freeze it off. And that's what you would like to want in the screen of your office or in a car or something like that. On the other hand, if we actually put more contacts and put smaller squares, we can make a display. And we can display an image there and change the image with time.
What makes this better than what's currently perhaps being developed or even in use?
Currently, in all displays, in television and in laptops, you use ITO, which is indium tin oxide, or some similar material. These are becoming very expensive. In fact, most of the cost of the laptop is in the screen itself. And also there's another very obvious implication that if you take your laptop and you bend it, it breaks. On the other hand, this one is made of plastic with graphene on the top. Graphene never breaks, and so it's flexible and works.
So how far away are we maybe from actually seeing these screens in use?
You see that here with a team of just a few people, a collaboration between 2 groups, we can make already quite large bendable screens. In the same time, in Korea, Samsung has made larger screens based on a slightly different concept. And so the prototypes are already here. And I believe that in the next year or so, there will be already some prototype mobile phone based on this screen. And then the real question is, will this go to market? And unfortunately, that's something that I cannot answer. You need to ask a company about that.
That was Andrea Ferrari and Antonio Lombardo explaining how graphene can be made from graphite and sticky tape, well as demonstrating the proof of principle that it could make really good flexible screens.
And if you'd like to know a bit more about this, you can find a video of this sticky tape method in action. That's at thenakedscientists.com/engineering.
And of course, Naked Engineering is supported by an ingenious grant from the Royal Academy of Engineering.
Now, using sticky tape is just one way of getting some graphene, and it's not likely to be much use as Andrea was saying, for Samsung making television screens. Exactly how graphene is made may well depend on what it is that you intend to use it for. So to explain more, we're joined by Dr. Carl Coleman. He's from the Department of Chemistry at Durham University. Carl, thank you ever so much for joining us.
Pleasure.
How do we make graphene in larger quantities? Sticky tape is all well and good for doing physics on graphene, but how do we make it in bigger quantities, in bulk?
Yes, I mean, as you can imagine, using sticky tape is a bit labour intensive if you wanted a large volume of the material. There are a number of ways to make it, and we sort of categorise those, I guess, as two camps. A top-down approach, which the sticky tape method would be a top-down, so that's starting from graphite, going to the thin layers, and then a bottom-up approach. So top-down, you can actually use a chemical method to really replace the using of the sticky tape. So there are people out there who basically, they take graphite and they do a rapid thermal expansion in the presence of an oxidizing acid such as sulfuric acid. That breaks apart those layers, and that also gives you the single sheets. So that's another way of producing it, and of course you can sort of imagine that being a little bit more scalable.
So effectively, by superheating a block of graphite, rather than peeling layers off, you're causing the layers to break apart spontaneously.
Exactly. So just give it a big kick in energy, the oxidizing acid, split those layers apart, and you'll get some single sheets. It's a little bit more difficult to separate, of course, because you'll have lots of graphitic impurities in there as well. So there's lots of processing that's necessary. So lots of centrifugation, dispersing in solvents. So there are other hurdles to overcome using that method. If you go to more the bottom-up approaches, which you can see or potentially see as more scalable, these we're talking more sort of CVD, that's a chemical vapor deposition approach, and there you can actually decompose pretty much any hydrocarbon-containing gas that you like methane, ethane, propane, etc. People tend to prefer methane, but you can use a mixture of methane and hydrogen and literally flow it over the top of a metal catalyst. And what the researchers in graphene like to do at the moment is use nickel or copper being perhaps the most prominent. And you can grow a graphene film by that decomposition of the methane and hydrogen on top of the copper. And I believe that's what Samsung are using with the Korean scientists to grow very large, tens of centimetre graphene films. So that's a little bit more scalable and easy to use than sticky tape.
And rather than using something that's becoming relatively rare as it gets used too much, the indium that we're seeing in current screens, using copper, which is quite common and still relatively cheap, and something like methane or any hydrocarbon, of which the prices are slowly going up, but we do still have plenty.
We do still have plenty. I mean, that's another issue about using fossil fuels, I guess. But yes, we do have plenty of natural gas kicking around. So using natural gas, you need hydrogen in there. You need a reducing atmosphere. That's the key. And copper is perhaps the most useful because the solubility of carbon in copper is quite low. This is one of the reasons why you tend to grow only one or perhaps two layers on top of the copper substrate. It's not without its own difficulties, of course, because you'd have to remove the copper. Because the whole idea of replacing indium tin oxide, ITO, of course, is to have a transparent electrode, and copper isn't transparent. So you would need to remove that copper, and so it's usually an etch to remove the copper, and then you can transfer the film, the graphene film, onto your plastic to assemble your plastic electronics.
So they're still fairly complicated methods that we have to create it. Are we looking at the moment that there is one great way of doing it and several not so good ways, or do they each have advantages over the other depending on what product you actually want? Yeah,
it really depends on what you want to do, and that will really dictate what method you want to use. The micromechanical method, i.e. the Scotch tape, sticky tape, is very good for physicists. They need a small little chunk of the graphene or a small sheet, and they can study it, measure it, and do lots of different things. The displays obviously is a little bit different, so you are going to need something like a large piece of copper foil to grow your film on, but then you have to transfer it from that copper onto your plastic and remove the copper. So, yeah, I mean, if you wanted the ITO replacement, that would be the method you would use. But if you were to use it in, say, composite materials, and there's a lot of work going on at the moment about using graphene in composites, so as a nanofiller, then of course neither of those methods would be suitable, and so we need another method to make the graphene. And there are variations on CVD to do that, so where you don't actually use a copper foil, use other metal catalysts, or use a spray pyrolysis type approach to get basically graphene powder that you would then be able to disperse in your polymer matrix to make your composite material. It does really depend on what you want to do with it.
Composites are relatively new. We haven't been using them for that long, but they've made huge waves in the aerospace industry. We've had a question from David Whaley, who got in touch via Twitter. He wants to know if graphene is likely to be used in spacecraft. I'd imagine it's composites that we'd be looking at there.
It definitely would be composites. On its own, it would be difficult to use in the aerospace. So it'd be incorporated into some sort of polymer matrix. So yes, I mean, there's lots of carbon-based nanofillers. So of course, we're all familiar with carbon fiber, which is perhaps the most common one that's out there at the moment, and carbon nanotubes, which have been making some headway, but of course there are some problems associated with that. But really, people have been looking there at these one-dimensional high aspect ratio materials as fillers. And then graphene has sort of come along and sort of challenged, really, I guess, carbon nanotubes in the prospect of being a carbon fiber replacement. So you'd have to get it into some sort of polymer matrix, so a resin or a thermoplastic. And really, the difference, I guess, with the nanofillers is you require much less of the nanofillers compared to, say, carbon fiber. And so that opens up a whole new game for the guys dealing in composites and how they process the materials, how they mold complex shapes, etc. So it opens up new doors, perhaps, that you wouldn't get with carbon fiber. But you'd still get the high strength to weight ratio that you would need from a composite material.
Well, thank you very much. We'll have to leave it there. That was Carl Coleman from Durham University. He's with us for the rest of the show, so if you have any questions for him, get them in on Twitter. That's @NakedScientists.
Graphene seems to be a very versatile material that we should soon see turning up in a range of applications. Now we're joined by James Torr, who's Professor of Chemistry, Mechanical Engineering, Material Science and Computer Science at Rice University, which is an incredibly impressive list. James, thanks for joining us. So what is it about graphene which makes it so useful? What its properties are there?
Well, it's certainly projected to do many things. I think certainly from the electronics perspective that it can carry an enormous amount of current, far more than copper or gold for similar-sized structures. It has a very high mobility, which means that you could build very fast switching devices, and that's really important if you want to be able to do high-performance computing. The numbers are just frighteningly high. If you consider a mobility of about 500 for silicon, graphene has been shown to be up around 1 million. So it could have operate with much faster switches, and then also on the display side. But then as we just heard, composite side and fluids, also working in conjunction with fluids.
So you were talking about mobility then. So what actually is mobility?
So I guess a way you can imagine this is if you switch a device and you move the carriers all in one direction, so they're propagating across, you have to wait for those carriers to get across to get your message across the silicon. So you can't switch it back the other way until the carriers have gotten all the way across in one direction. So there's a time delay. You can't switch it as fast as you'd like. You have to wait for things to get across it. But if things can get across extremely rapidly, then you could keep switching far more rapidly and you could build much faster switches.
So a major limit on the speed of a computer chip at the moment is just the time it takes for the signal to get from one side of the transistor to the other side of the transistor. And graphite, you were saying, was more than 1,000 times faster than silicon.
That is correct.
How difficult is it going to be to build a computer chip out of graphene?
You can certainly build one transistor. Lots of people are doing that. But certainly in our computers we have billions and billions and billions of these, tens of billions, hundreds of billions of them. So nobody has solved this one yet. But the nice thing about graphene, which you couldn't get with carbon nanotubes, is that graphene, if you make a sheet of it, you can chop it up using resists and light much like you do silicon, so you can pattern in that way. So you make a large area and you chop it up into the smaller pieces that you want, and that's something you could never do with carbon nanotubes. The problem still remains, however, in that it's a planar structure, and generally what you want to be able to do is build vertically. So it's analogous to having straws. If your straws were laid out on a surface, you could only get so many, but if the straws are standing up, you could pack a lot more. And right now, silicon is assembled vertically and not horizontally, so that you can get more on a chip, whereas graphene is predominantly horizontal, and that's the way it's going to be until we get better at growth methods and transfer methods that might allow it to be vertical. So there's still many hurdles that need to be done before this is going to begin to rival silicon.
So at the moment with graphene, even with something as simple as making one wire across another, would be very difficult.
No, you can make one wire across another. Graphene would be good for that. But in a vertical array like silicon, then it's hard. But that's taking on silicon at the high-end electronics, and that's not really fair to graphene, because silicon has had 50 years of work on it, and that is probably millions and millions of person years put into it, and many, many trillions of dollars or pounds put into it. So there's a lot of development that's gone into silicon. Graphene has a fundamental property that's really quite amazing, and in lower-level applications it's going to compete quite well, such as in the touchscreen displays that we've heard about. Being able to roll these things up and fold them up, which would be quite nice, so that when you drop your iPhone, you don't have a cracked screen, which is a real headache for the user.
Because up till now, the standard transparent electrode is indium tin oxide, which it's sort of ceramic, isn't it? It's very brittle, whereas I guess graphene is so thin that it's got to be flexible.
Yeah, it's flexible, and so that you can put it on a flexible substrate, so that you could think of rolling up your iPhone and putting it behind your ear like a pencil or whatever and walking away. I mean, that's certainly the possibility.
So you can actually make all of electronics with graphene. So, a graphite behaves like a metal. It just conducts electricity. So can you turn graphite into a semiconductor as well as a conductor?
Right, so that's a good point. Graphene is a metal, and it has a band gap that's zero or near zero. So you have to turn it into a semiconductor. But that can be done. That can be done by putting in impurity atoms into it, and then you can begin to open up a gap. We don't have the absolute control over that we'd like, but researchers are getting tremendously better at that all the time. So I think that's going to open up. But I don't think that's going to be the forefront of applications. I think the applications are going to insert in an even easier market than mainstream electronics.
So this is going to be all the transparent stuff. In fact, Barry Freeman was saying, is graphite going to be commercially viable anytime soon, and when will we likely to see it used?
Well, again, I think some of the simpler applications are, for example, one of the things that we're working on, we're taking both graphene and the oxidized version of it, graphene oxide, and putting it into drilling fluids that are used to drill holes in the ground where they find oil. And one of the problems is the fluids infiltrate the rock, and then when you try to yield the oil from the rock, the rocks have often been plugged, and they have to go back in and try to wash these fluids out. And so we found that if we could add the graphenes in oil-based drilling fluids or the graphene oxides in water-based drilling fluids, that these act as little nanofilters and keep the drilling fluid from infiltrating the rock. So this is a very simple application. So anytime you're talking about nanotechnology, you have high-level applications, and then you have simpler applications. So you have both active applications where you're asking a lot of the material. You're asking it to have a mobility. You're asking it to accept an electron and spit out a photon, for example. Or you have passive applications where just its mere presence being there, acting as a filter in something that it's a very passive application, then it can insert far more easily into the industry. And I think that's where we begin to see the initial applications. And again, a composite is a passive application. Its presence being there causes the composite structure, the molecules in the composite generally to be stiffer because they have to align past the nanostructure, and that increases the performance of the composite in that way. So the simpler applications will always insert first.
Brilliant. Thank you very much, James. That's wonderful. That was Professor James Torr from Rice University.
This is The Naked Scientist with Ben Valsler and with Dave Ansell. Now, Dave, we've had a question from Carol King on Facebook. She wants to know if graphene could be converted to diamond-phene. What do you think?
Okay, I'll start off with diamond and graphite, the large-scale structure, three-dimensional structures. Graphite and diamond have got incredibly different structures, even though they're both just made out of carbon atoms. In graphite, you've got a whole series of planes made up of hexagonally arranged carbon atoms, all tessellating together with an atom where all the hexagons meet. Whereas diamond is this tetrahedral structure with each carbon atom being bonded very strongly to four others at the corners of a tetrahedral pyramid, so a triangular-based pyramid. This is the reason why diamond is incredibly strong. It bonds in every possible direction, whereas graphite only is very strongly bonded inside the planes, but very weakly between them, so they slide across each other, and it's quite a good lubricant.
So if you wanted to convert between the two, you actually have to break and then remake quite a lot of bonds, so it must be quite an intensive process.
Yeah, that's right, and diamond is only actually stable under very, very high pressures. The stable form of carbon at room temperature and pressure is graphite. So in order to do that, in order to convert graphene or graphite into diamond, for a start, you'd have to use incredibly high pressures. And also diamond is an intrinsically three-dimensional structure, so a single plane of it, so equivalent of graphene, wouldn't really make sense. It would be incredibly unstable, and it would immediately convert back into something like graphene or just fall apart.
So graphene in itself isn't a better source for making something like a flat sheet of diamond. You may as well just use any old carbon kicking about.
Yeah, that's right, and it's probably a lot easier to get it from some kind of gas like methane or something in a CVD process like they were talking about making graphene earlier.
We still have with us Dr. Carl Coleman from Durham University. Carl, we've had a question on Facebook from Silfa Zoidberg who says, I don't understand why graphene is considered to be two-dimensional. One atom thick still is one atom thick. What do you think about why do we call it two-dimensional when clearly it has a third dimension?
Yes, I guess you could argue it has a third dimension, but really one atom thick is really as thin as you can go. So I would argue that it's negligible in thickness in one direction, and that's why we truly call it a two-dimensional material. And graphite, of course, would be the three-dimensional version, where you have several layers that make up the structure. So basically, you can't get thinner than one atom, I would argue.
And I guess also the electrons actually have a wavelength, so affect something a bit like a size, and the wavelength is of the order of the thickness of the graphene. So to the electron, it does look like a two-dimensional thing because it's as thick as they are.
It is. It's confined in that two dimension. You're right. Yeah.
Thank you very much. We also still have James Torr on the line. James, we've been asked again on Facebook. Tom Curl and James Passas both asked how graphene compares to Buckminster fullerene. These are buckyballs, which apparently was supposed to be a wonderful lubricant, but turned out to be too sticky.
The nanostructures, if you have a buckyball, that's considered zero-dimensional, even though it does have dimension, but it doesn't reach out in different directions. If you have a nanotube, that's considered one-dimensional. It's extending in one direction, and in the other direction, it's only about a nanometer wide. But fundamentally, we just heard the discussion, but it's considered one-dimensional, whereas graphene is like a sheet. It's two-dimensional. The fullerenes, it turned out in high compressive operations, they would actually tend to decompose in many structures, and that's why they're turned out not to be very good lubricants. Whether graphene is going to be a great lubricant, I don't know. Graphite, the three-dimensional structure, is a good lubricant because it's able to shear off lots and lots of sheets of graphene, which is really what makes it slippery.
So the sheets themselves slide past each other. This is also why they make good pencil lead.
Correct. And whether a sheet of graphene would make a good lubricant, I rather doubt it, in the sense that you don't have that ability to slide past itself. It's only one atom thick.
Thank you very much. That was James Torr from Rice University. And now it's time to join Diana O'Carroll with our question of the week.
This week, try attaching yourself to the fridge door for this question.
Hi, Naked Scientist. It's Alan Blake from London. I have a question for you, please. I received a brochure advertising all things magnetic and claiming to cure all sorts of ailments like snoring if this object was put up the nostrils, and all sorts of aches and pains if worn on different parts of the body. Please can you advise me if there is any evidence at all to prove that magnets have these type of powers, and if so, how they work? Thank you.
How magnetic are we, and do ferrous magnets have an effect on our health?
My name is Stuart Richmond. I'm from the Department of Health Sciences at the University of York. The fact that blood contains iron is one of the reasons why some people believe magnetic bracelets might have an effect on the human body. However, blood is not magnetic in a conventional sense. In other words, it's not ferromagnetic, which is what most people understand as magnetism. If blood was ferromagnetic, then people would bleed to death or explode in MRI scanners, which produce much stronger magnetic forces than those of magnetic bracelets. So, although deoxygenated hemoglobin is paramagnetic and very slightly attracted to a magnet, and also both oxygenated hemoglobin and plasma are diamagnetic, or in other words, slightly repelled by a magnet, in theory, wearing a magnetic bracelet shouldn't have a physiological effect. Firstly, any influence on the polarity of ions within red blood cells would be lost because blood flows in a pressurized and turbulent way. Secondly, blood is warm, so for any paramagnetic effect to occur, it would need to overcome the forces of Brownian motion, all of which are extremely unlikely. So, returning to the second part of the question on do magnetic bracelets actually work, in my research on magnet therapy and arthritis, I began not by asking how magnetic bracelets might work, but rather by testing whether they had any health effects on humans and by trying to control for the power of imagination. The best available evidence shows that magnet therapy lacks any meaningful effect other than a placebo effect for arthritis and pain control. Although there are some contradictory results, it would appear that for those trials which have shown a benefit, they've also tended to suffer from problems of blinding, which might explain those findings.
And when he says the test subjects weren't blind, that means that they were able to identify if their bracelet was magnetic or not, potentially altering the outcome of the trial.
So, despite this, the effects of positive suggestion should not be discounted. If people choose to believe that wearing a magnet might help, then it may well do. Although there are no known side effects, the danger is, however, that people may use magnetic bracelets instead of other clinically effective treatments.
So magnetic jewellery hasn't as yet been conclusively proven to reap health benefits upon their patients. But something should be said for the placebo effect. Sometimes just believing that something works can make you feel better. On the forum, Steve Fish commented, "If the magnet doesn't stick to you, it won't do you any good, but if it does stick, run screaming." And Clifford Kay said that it is possible to polarise hydrogen atoms in water using a magnet. Indeed, one group of researchers made animals levitate using this phenomenon. Next week, prepare for those Christmas parties.
Hello, my name is Shane, and I've got a question. My question is, why is it that some people are very, very photogenic, while other people are not quite as easy on the eye, to put it politely? Thank you very much.
Why is it that some people manage to look great in photos, even if they're pretty ordinary in real life, while some look awful when they're quite good looking, and others, like me, look uglier than a blobfish that's graduated from the hideous college of repugnantness and then been beaten several times over the head with a tasteless piece of furniture that has been stuffed full of models of the world's ugliest car, which everyone knows is the Fiat Cubo? Answers on the forum at thenakedscientists.com/forum or email Chris at thenakedscientists.com.
I think Diana is being unnecessarily harsh on herself there. She looks lovely in photographs. But if you think you know why it is that some people look good in photos and some people don't, regardless of how they look in real life, then do get in touch. You can email Chris at thenakedscientist.com if you have any ideas. But that's all we have time for this week. Next week, we're getting festive with our Christmas special. Chris, Kat and Dave will be back as we explore the science of cocktails. If you've got any questions for us, you can tweet at Naked Scientists. If you'd like to catch up with anything we've done, just join us online at thenakedscientists.com. Many thanks to Dr. Carl Coleman and Professor James Torr for joining us, and to our production team, Tom Simpkins, Mira Sentherlingham, Louise Ogden and Diana O'Carroll.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at nakedscientists.com.